Reinforcement learning (RL) is a machine learning paradigm grounded in the framework of Markov decision processes (MD). It enables an agent to learn an optimal policy through trial-and-error interactions with an environment. The agent performs actions and receives feedback in the form of rewards based on the consequences of those actions. These reward signals guide the agent to iteratively refine its policy in order to maximize the cumulative long-term reward. RL is built upon several key components: agent environment, state action reward policy value functions, including the state value function and action value function. Reinforcement learning can be integrated with planning algorithms, for example, Monte Carlo tree search, MC, model predictive control (MPC), achieving high efficiency in structured environments. In such contexts, it supports interpretable, controllable, and verifiable reasoning. RL demonstrates exceptional capabilities in exploring continuous action spaces across temporal and spatial dimensions, and it learns autonomously through direct interaction with the environment. More powerfully, RL agents can engage in continuous interaction with real-world environments and reflective learning, exhibiting the potential for lifelong learning. However, RL faces significant limitations. It struggles to scale to large or continuous state spaces. Generalization capabilities remain weak. It has difficulty processing high-dimensional perceptual input. It lacks effective mechanisms to incorporate prior knowledge or hierarchical structures. Adaptability to dynamic environments is limited. On the other hand, neural networks are known for their strong ability to approximate arbitrary functions and retain memory. However, due to the typically singular nature of their output and limited feedback signals, neural networks lack strong exploratory capabilities in temporal and spatial dimensions. In a certain sense, reinforcement learning extends the feedback mechanisms of neural networks beyond simple single-output responses. When neural networks serve as the foundation for reinforcement learning, they significantly enhance the agent's adaptability to dynamic environments. This resembles how the brain coordinates with limbs. The brain develops optimal strategies, while the limbs execute actions based on those strategies. This reflects the essence of evolutionary adaptation. An intelligent entity, in principle, must possess mechanisms for action. Aquatic creatures have fins and tails. Many microorganisms possess flagella. Intelligent systems, too, must develop mechanisms to act upon the world. Adaptation may occur not only outwardly but also inwardly. Neural network-based reinforcement learning can absorb external environmental knowledge to construct an internal world model. Through internal exploration, planning, and abstraction, such systems can distill a minimal, yet essential cognitive core, avoiding the need to memorize vast amounts of redundant data. These memory systems may rely on associative memory or employ mnemonic techniques akin to the method of loci, for example, Matteo Ricci's memory palace. Note: since reinforcement learning can be interpreted as an extension of feedback mechanisms in neural networks, neural network methods in the following discussion refer collectively to RL and related approaches. Nonetheless, current neural network systems receive far more limited feedback than biological organisms. For instance, they lack the ability to perceive or express facial emotions, fear, injury, or disease, experience reproductive drive, or suffer from anxiety. However, they are also not constrained by biological survival pressures, such as the need for food or shelter. They can be optimized with arbitrarily defined reward functions and can learn from data that may be completely unintelligible to humans. One might imagine a future where such systems can communicate not only with humans but also with animals, or even with cells. Note: the notion of feedback here is generalized. It includes not only scalar rewards but also classification errors, bounding box deviations in object detection, autoregressive prediction mismatches, and other forms of error signals. These feedback signals can be modeled through neural networks, enabling representations of tactile sensations, gustatory feedback, and more. Importantly, they allow for integrating diverse environmental feedback, each assigned varying degrees of attention through mechanisms such as attention weights. It remains an open question whether current neural network methods follow any underlying learning principles or philosophies during training. Such principles are often what allow humans to learn more effectively. These may include the Feynman technique, awareness of psychological fallacies, and insights from classical works such as the Tao Te Ching. Despite their impressive capabilities, neural networks exhibit limited adaptability, analogous to the constrained adaptability of biological organisms within a finite timescale, i.e., limited rate of change. The I+1 learning hypothesis proposed by psychologist and educator Stephen D. Krashen, discussed in the essay Sleep and Cervical Vertebrae Health, offers inspiration for gradual knowledge acquisition in neural systems. A more detailed discussion of adaptability can be found in the paper Simulated Algorithms for Lives: Genetic Stability and Evolutionary Control in Neural Networks. One major challenge in training neural networks is the instability of parameter convergence due to stochastic gradient updates, resulting in non-deterministic outcomes across multiple training sessions. This raises concerns about the stability of learned representations. To maintain a form of genetic stability analogous to biological inheritance, network execution behaviors could be compared against a reference model akin to comparing against a genetic blueprint. This might involve metrics such as Kullback-Leibler, KL divergence, or applying Lipschitz constraints, ensuring that the trained model does not deviate excessively from its original form. Minor low-probability mutations, i.e., local model adjustments, could be allowed and controlled within this framework, enabling a balance between global stability and local randomness. This mirrors the evolutionary balance between genetic conservation and beneficial mutations. I personally believe that neural networks represent a unifying framework for understanding evolution. Though the current methodologies remain incomplete, many of the essential components have already emerged.